Hi, my name is Tom Hoeffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about the hybridization of the central atoms. The reason we need to talk about this is because if they do not hybridize, we will not get the shapes that we learned with our valence shell electron pair repulsion theory. So let's get right into it. Okay, what we're going to do is we're going to investigate the central atom carbon, okay, in CH4 versus CO2 because they do different things when they hybridize. Now let's talk about the bonding of CH4. In a previous video we did CH4 and we found out that it has 4 domains and it makes this tetrahedral shape with a bond angle of approximately 109.5 degrees. So all tetrahedral shapes will kind of make 109.5 between all of their non-central atoms. Now, if we take a closer look as to what the orbitals of a carbon look like, we find out that it has a 1s orbital, a 2s orbital, and actually all the elements in that 2p block from boron to neon, and that's where carbon lies, okay, is going to have a px, which means a p orbital on the x-axis, a p orbital on the y-axis, and the p orbital on the z-axis, which would really be coming out of the board and into the board. I kind of did it at a diagonal just to try to fit it in there. But if you want a three-dimensional look of how the p orbitals look like, this would be the p orbital on the x-axis. And remember, they'd be lobes, not water bottles, okay? But the p orbitals would be on the x-axis, the y-axis, okay? And then the z-axis is this coming out towards you and coming like kind of like into the board if we're looking at this three-dimensionally, okay? Now, when we look at these p orbitals, the x and y axis is at 90 degrees, the x and z axis is at 90 degrees, and the y and z axis is at 90 degrees. So that's kind of interesting because if these p orbitals are involved in bonding, of which they are, okay, then how do we get a bond angle of 109.5 according to our valence shell electron pair repulsion theory? The answer is these p orbitals have to be unlocked, okay? And when they're unlocked, then they can spread out according to valence shell electron pair repulsion theory and get different angles like 109.5 in the tetrahedral. So the reason hybridization occurs, it's to unlock the bond angles so that we can follow our valence shell electron pair repulsion theory geometries, like the tetrahedral. So let's take a closer look as to like what happens in hybridization in carbon to make this tetrahedral shape. And if we look at the electron configuration for carbon, it's 1s2, 2s2, 2p2. So the 1s orbital is filled, the 2s orbital is filled, and then up here we have the 2p orbitals, and we have 2 electrons in the 2p orbital. Okay. If you're unfamiliar with electron energy diagrams, you'll need to go to Unit 2 playlist to find a lesson on electron energy diagrams, because we're using them here in the Unit 3 playlist to describe hybridization. So if you're unfamiliar with this, you might want to click back to Unit 2 and watch a video on energy diagrams for electrons, okay? But this is kind of how, you know, a carbon atom would look like. So it would have this 2 sphere, and then we have these p orbitals, and these p orbitals are at 90 degrees, okay? Now, if we look at hydrogen's energy diagram, it's very simple. There's just like one electron in the 1s orbital, okay? And to make a covalent bond, these orbitals have to overlap, okay? It's electron orbital overlap is actually what a covalent bond is. So this hydrogen electron would come into here to fill up this orbital, and that's actually what makes the covalent bond. So when we investigate carbon just a little bit more detail, in this ground state electron configuration, to me, it looks like carbon can only make 2 bonds. Overlap in this one where it's unpaired, and overlap here where it's unpaired. That's where electrons can come in to bond. So the way I see it here, it looks like if we have hydrogen atoms it could only make two bonds with carbon. But when we look here, when we look at CH4, okay, there's 4 hydrogen bonds. So how does that happen? Well, it means that these orbitals have to hybridize, okay? And there's 2 steps in a hybridization. The first step is electron promotion. What I'm going to do is I'm going to move an electron from here to here and then explain why I did that, okay? So the next phase, okay, the first step is going to be electron promotion. And when I do that, my energy diagram is going to change a little bit. Nothing happens to the 1s, okay? However, we are going to promote that electron from the 2s into the 2p. So what I did here is I just took this electron and I put it right here. Sometimes people ask me about the spin. It was spinning down, now it's spinning up. That doesn't matter, okay? If there's only 1 electron in here, doesn't matter if it spins up or spins down. These all could be spinning down. It would mean the same thing. Same thing for the hydrogen. It doesn't matter if it's spinning up or spinning up, down when it's by itself. However, when it does come down in here to bond, you got to make sure those electrons will be spinning in opposite directions. That's when it matters, okay? So our first step is to promote the electron, okay? Now, the reason why we did that, you can see, wow, I can make a bond here, 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 and here. I now can make 4 bonds, which is really important if we want to make CH4, okay? So the problem here, though, is if I have a hydrogen orbital, which is actually a circle or a sphere, come in here, and it's going to come in here to overlap somewhere. If it overlaps, like let's say right here, okay, it's actually overlapping 2 orbitals. It'd be overlapping the 2s orbital, and it would also be overlapping the 2px orbital, and that can't happen, okay? When you have orbital overlap, it has to occur just between 2 orbitals, okay? So in addition, okay, we want to make sure that all these orbitals are the same energy. So what happens is that the s orbitals and the p orbitals, they're going to hybridize. And what happens there is that they become like equal in energy. So I'm going to pick a line that's kind of like somewhere in the middle, okay? And instead of having 2 different energy levels, I'm going to have them all at the same energy level between the S and P. So kind of like right here in the middle, 1, 2, 3, 4. Now I have 4 energy levels that are all the same, and we're going to call this sp3 hybridization. Okay, now I'm going to tell you the type of hybridization is going to depend on one thing and one thing only, and this is probably the most important part of the lesson, okay, is that it's going to be the number of electron domains. So if we come back here and we look at the carbon and we count the number of electron domains, 1, 2, 3, 4, there's 4 electron domains. So that's why I decided to hybridize all 4 of these orbitals. If this number was 2 or 3, I would not have grabbed all of these orbitals. I would have only grabbed 2 or 3 of the orbitals to do the hybridization part. So once again, the first step is electron promotion, and we get the electron out up to here so that it can have 4 bonds, okay? And then the second step here is what we call the hybridization. And what we do is we count the number of electron domains. In this case, there was 4. So I grabbed all 4 of them, okay? And I kind of like evened out their energy, okay? So that I have 4 equal orbitals. Now, if there's 4 equal orbitals, then valence shell electron pair repulsion theory can work, okay? So what this did during the hybridization, this is where the angles get unlocked. The orbitals are no longer the px, the py, and pz at 90 degrees. They're now sp3 hybridization, and they will spread out according to valence shell electron pair repulsion theory, okay, to form this tetrahedral at 109.5 degrees. And that can only happen if you have 4 orbitals, each with an unpaired electron, that are all equal in energy. Okay? And that being equal in energy is really important. That's the hybridization piece. Okay? So let's take a look at a different molecule. Let's say we didn't have CH4 and instead we had CO2. Okay? And I want to show the bonding for CO2. This would be our drawing for carbon dioxide, or CO2. If you look here, it no longer has 4 domains. It has 4 bonds, but it only has 2 domains. Remember, an electron domain is an area that's dense in electrons. So we got a domain here and a domain here around the carbon. Well, if there's only 2 domains, then how does that change the hybridization piece? Okay. Well, the first part doesn't change at all. There's always going to be that promotion of the electron, but this hybridization piece is going to be different in carbon dioxide than it was for CH4. Because there's only 2 domains, I am not going to grab all 4 of them. I am only going to grab 2 of them. Okay? So the 1s is the same, and the part that I'm grabbing is just 2 of these orbitals, and I'm going to put that in the middle, so kind of like right here. And since I only grabbed 2 orbitals, that means I grabbed 1 s and 1 p, so this orbital is going to be called sp. Remember, in CH4, I grabbed them all, so it would be s and then p3 because I grabbed all 3 of them. Okay? But in this case, I'm only grabbing 1 of the p's, so it's just sp. That's the hybridization piece, okay? And that's where the electrons are going to bond for their first bond. Now, you might be saying, what happens to these 2p? Nothing happens. They're still there. So I'm going to keep them on the same level here. And we're still going to be able to make 4 bonds, okay? But the first 2 bonds are going to be sp hybrid orbitals. And those are going to be the single bonds. And sometimes those single bonds are also called sigma bonds, okay? And then these other 2 bonds are going to be for the double bond. And when you double bond, sometimes we use the symbol pi, okay? So remember, this is lowercase sigma and this is pi to talk about the bonding, okay? So in in carbon dioxide, CO2, okay, it's going to be sp hybridization. And if there's only 2 domains, remember, that's going to make the linear shape because this is linear. Okay, so we get orbitals that make 180-degree angles, and then these other p orbitals are going to be used to make the double bonds. So hope that helps you with hybridization. Remember, just quick review, the first step is always electron promotion. That gets all our electrons spread out as much as they possibly can be, and that's so that we can make more than just a couple bonds, okay? But then, because we want them to get unlocked from 90 degrees, it goes through this hybridization, okay? If you want linear shape, you need 2 equal orbitals, okay? So it's going to be sp hybridization. That'd be for 2 domains. If you wanted 3 domains, you would grab 1 s and 2 of the p's, and then you'd have sp2 hybridization, and that would be trigonal planar, okay? If you grab all of them, that's going to be sp3 hybridization, like we did with CH4, and the shape that you'll get out of that is tetrahedral, okay? So the shape, number of electrons, and the type of hybridization that occurs are all related, okay? And if that helped you learn hybridization a little bit better, okay, please like and subscribe, as that will help the YouTube algorithm get this out to other students that want to learn chemistry in a straightforward fashion.